This is question 3.7. This is a slightly long question. Let me read it out for you first. The interval rule of hyperfine structure states that the energy splitting between two levels in a hyperfine multiplet is proportional to the larger of the F values of the levels spanning the gap. Then we have these three parts. Part A, explain the origin of the rule. So basically we need to somehow derive this rule, or at least give an intuition as to why this rule is true. Part B, deduce a similar rule for the splitting of the fine structure levels. So this was for hyperfine structure levels, and similarly we have to find for the fine structure levels as well. And part C, the 3p 2p 3 by 2, this is the spectroscopic notation that we saw previously. The 3p 2p 3 by 2 level of sodium consists of 4 hyperfine levels with splittings of 60 megahertz, 36 megahertz and 17 megahertz. These are the splittings between them, between the 4 levels, 4 hyperfine levels. And within this part C we have subparts. So essentially we have 5 total parts to this question. Subpart 1 is explain why it must be the case that I is greater than equal to 3 by 2 and find the value of I that fits best to the observed splitting. So I is the nuclear spin, and let us now look at the solution for this problem. So let me get my pen. Part A. So this we need to find out the energy gap between adjacent hyperfine levels, that is the energy splitting between two levels. So the energy gap between adjacent hyperfine levels and the levels can be denoted by I and J. So that is given by, so delta E will be delta E corresponding to the hyperfine splitting, the hyperfine splitting for the configuration I, J and F. Note that F is I plus J minus the corresponding hyperfine splitting energy for I, J and F minus 1. So these are the two adjacent levels. So F, as you know, takes integer values for j minus I, mod of j minus I to mod of j plus I. So if one value for f is there, then the lower value of f or the next value of f would be f minus 1, because integer values are taken in step sizes of 1. So this is what we need to find out. And we know that this delta E for hyperfine splitting, we are given, let me write down. So we are given that this hyperfine splitting this is a constant which is j dependent, h cross squared over 2 times f into f plus 1 minus j into j plus 1 minus I into I plus 1. So when we put it back into this delta E, so delta E is, let me just make use of this delta E hyperfine splitting energy. So this is the following. I'm just substituting this value into this expression. This minus of, again, these constants as it is, and this time f is not just f, it is f minus 1. So f minus 1 and f minus 1 plus 1. So this is f minus 1 plus 1, that is nothing but f itself, and j remains the same, and so does I. Let me rewrite it a little bit smaller so that it fits into this one row. Okay, great. Now we can take terms common. So we know that these constant terms will then cancel out. So since j is the same, so this will cancel out, and I is also same, this will also cancel out. This finally leaves me with the constants, this, and we have f into f plus 1 minus f minus 1 times f. So let me simplify this further. So this gives me f squared plus f minus f squared, and minus minus makes it plus, plus f. Again, f squared cancels out, so we are left with 2f, and the 2 of the numerator cancels out with this 2 in the denominator in this h cross squared by 2. So finally I am left with the following. So as you can see, because of this term, this energy splitting is proportional to the value of f of the higher level, of the upper level. We had taken, remember, we had taken f and the lower level f minus 1 and the energy difference between that. So we have shown that delta E is proportional to f, which is the upper level. So we have shown part 1 that the interval rule of hyperfine structure states that the energy splitting between two levels in a hyperfine multiplet is proportional to the larger of the f values of the levels spanning the gap. So here we have f and not f minus 1. So it is proportional to the larger f value which we had taken, which was f in this case. So that was part 1. Now in part B, we need to, so we just did part A, and part B is to deduce a similar rule of splitting for the fine structure levels. So this was for hyperfine structure levels. Now we have to repeat for fine structure levels. And note that the fine structure levels and hyperfine structure levels are very similar. So let me write down the expressions for fine and hyperfine, and let me show you the similarity. So in this hyperfine, for hyperfine, we made use of F is J plus I, so this gave us that the energy for the hyperfine splitting, hyperfine structure, was proportional to, apart from the constants, so that's why I'm writing proportional to. So ignoring the constants, this is proportional to the following. And this comes from finding the J dot S term. If you find this J dot S and take the ensemble average of that, you get this what we just wrote. And again, this because you can write this J dot I as half of J squared minus L squared, minus you can write it as F squared minus J squared minus I squared. So doing this gives you this F into F plus 1 minus J into J plus 1 minus I into I plus 1. Now in fine level, or it is also known as the spin orbit coupling, fine or spin orbit, what you have is, you have J equals L plus S, and note that I and S both are spins. I is the nuclear spin, S is the electron spin. So I and S are similar terms, and the analogy works out that you take J analogous to L over here. So working out the analogy, this delta E for the spin orbit or fine structure will be proportional to J times J plus 1 minus L into L plus 1. Note the analogy, this is completely analogous. I have replaced I with S, J with L and F with J, and this comes from the L dot S spin orbit coupling. This, if you write as one, this can be written as follows. And that's how you get this value for the energy. And so this you can see clearly is completely analogous. The hyperfine and fine energies are completely analogous, but let us, for the sake of brevity, repeat the process. So the energy for the fine or the spin orbit coupling is some constant, let me call it some constant C prime times J into J plus 1 minus L so this constant is basically some constant and then this h cross squared by 2 terms, so that's why I'm just replacing it by a constant. It's irrelevant in this particular question. And now we will look at the energy difference between adjacent levels, which will be the following. So L, S, J and then J minus 1. The lower level. J is the higher level and J minus 1 is the lower level. Again, J takes integer values with step size of 1. So J and then the lower value or the next value will be J minus 1. And J takes the value from mod of L minus S to mod of L plus S. Now once again, let's plug this in. So we have the following. J minus 1 now and then J minus 1 plus 1. L and S remain the same. So once again, these terms will cancel out, L will cancel out, S term will cancel out. This leaves me with C prime J to J plus 1 minus J minus 1 times J, because J minus 1 plus 1 is J, and simplifying I get J squared plus J minus J squared minus minus plus J. So J squared and minus J squared, they cancel out, and finally I am left with, and once again you can see this is proportional to J. The term that comes is J, which is the higher level, higher energy level. So just like the hyperfine structure, we deduced a similar interval rule for the fine structure levels. Now we move to part C. So let me draw the structure, the energy structure. So you have 4 levels. So this will be F equals to 3 and the next level F equal to 2 and then F equal to 1 and finally F equal to 0. This energy splitting we are given as 60 megahertz. Then the next one is 36 and then 17. This one is 36 and this one is 17 megahertz. So that's the frequency. You multiply it with h and then you will get the energy splitting. So this is the hyperfine structure. And we know F is J plus I. So F can take values from J plus I, mod of J plus I, to mod of J minus I in step size of integer. And the spectroscopic notation that we are given is 2p3 by 2. So 2p3 by 2. This means this is the J value. J is 3 over 2. Now there can be two cases. So if J is greater than I, then we have 2I plus 1 splittings, 2I plus 1 levels, and the other case, if J is less than I, then we have 2J plus 1 levels. Now J is given as 3 by 2, so 2J plus 1 will be 4. This is less than equal to I. And clearly we can see 4 levels. We are given 4 levels. So that means that the condition that we are in is this one. J is less than equal to I, because we see 4 levels. This means that I is greater than equal to J, which is equal to 3 by 2. Okay, so this was part C and the first part of part C. Next, part 2, find the value of I that fits best to the observed splitting. Okay. So we will make use of the interval rule that we just derived previously. So interval rule says that this energy splitting is proportional to the value of F for the upper level. So and this is nothing but delta E. So this splitting between the levels is delta E. So in our case we have from F equal to 3 to F equal to 2, 60 megahertz. That's the first delta E. So the splitting ratio, if we want to find out the splitting ratio, so if we want to take the ratio with respect to this bottommost splitting energy, this ratio with respect to this 17 megahertz, so splitting ratio so 36 over 17, that is 2.1. So 2.1 is to 1, and 60 divided by 17 is roughly 3.5. So 3.5 is to 2.1 is to 1. So this is the splitting ratio between these F levels. Now if we look at these F levels, if I equals to, let us say, the lowest value 3 by 2, because I needs to be greater than equal to 3 by 2. So if I is 3 by 2, then f, which is j plus I, and j is also 3 by 2, so f takes the value j plus I to mod of j minus I, and j is also 3 by 2 we are given from the spectroscopic notation over here. J is 3 by 2. So this means 3 by 2 plus 3 by 2, that is 3, then 2, 1 integer values, and finally 3 by 2 minus 3 by 2, which is 0. So these are the values of f that can be taken. And in fact, just I had even written it over here, but I should not have written it earlier, because that time I did not know that what the values of f are. So I should not write it. I just wrote it based on intuition 0, 1, 2, 3. But because we have not found it yet, we should not write it. This is experimental data. So experimental data is there. We do not know yet the values of f. We need to find out that by fitting. So you can clearly see that because delta is proportional to f, if I write down the values based on this, the splitting ratio will be 3:2:1, because we look at the higher value of f. So 3, then 2, and then 1. So that's the ratio, and you see that this quite matches well with the experiment. So 3.5:2.1:1, just slight error is there. So this matches really well. So in our case, I equals to 3 by 2 actually fits really well. So I can say I is equal to 3 by 2, and then I can actually label these as f equals to 3, f equals to 2, f equals to 1, and f equals to 0. Now, just to see that this is indeed the correct fitting, let us look at the next value of f of I. So I is 3 by 2, and then the next value of I can actually be 2, because I is nuclear spin, and spin takes values half. So next value of I will be 3 by 2 plus 1 by 2, which is equal to 2. And for this value of I, f will be, remember f is j plus I to j minus I, and j is 3 by 2. So 3 by 2 plus 2, that is 7 by 2, and then in step size of 1. So 5 by 2, 3 by 2, and finally j minus I. J is 3 by 2 minus I, so minus 1 by 2, which is mod of that is half. Now in this case, the splitting ratio so 3 by 2 over 1 by 2. Sorry, we will take the higher value of f according to this splitting, hyperfine splitting. So what we need to find out is 5 by 2 divided by 3 by 2. So that is 1.7. And then we have 7 by 2 divided by 3 by 2, that is 2.3. So you see clearly this is very much off. And okay, if in case you forgot, this ratio was actually coming by 60/17. So that's how we are doing. So similarly, 7 by 2 divided by 3 by 2, and then 5 by 2 divided by 3 by 2, and 3 by 2 divided by 3 by 2, that is 1. And 5 by 2 divided by 3 by 2 is 1.7, and 7 by 2 divided by 3 by 2 is 2.3. And you see that this ratio is very much off from this experimental ratio of 3.5 is to 2.1 is to 1. This is very much off, so this cannot be the best fit value for I. Sorry. So indeed the best fit value for I is 3 by 2. You can even then proceed to check for the next value of I, which will be 2 plus 1 by 2, and that is 5 by 2, and you can see that the splitting ratio energy will be even worse, and it will not match at all. So in this question we saw the hyperfine and fine levels and the splitting energy between them and the interval rule, and then we applied those interval rules to this specific case of sodium atom.